Hello and welcome to Beamerfolk.
On the bench before us, we will do a quick overview of the breadboard that I've assembled of the differential temperature sensing alarm. I'll go from right to left. We have here at the right hand side a sounder alarm. I've put a ball of blue tack on the orifice of the alarm to attenuate the sound, and a small capacitor which decouples the supply to the sounder. Next we have a boost converter. Well, as this is driven by 3 AAA batteries in a holder, and that represents about 4 volts, I felt the need to up that to 5 volts. I could have upped it further, it's just that the only one I had in stock was a 5 volt boost converter, and that's it there. Next along is a potentiometer. Well, that is the potentiometer that adjusts the alarm sensing threshold from about 1 degree C to about 16 degrees C. I've got this actually set at 5 degrees C for testing purposes. Next along is the TLC 272 op amp, which is in there. We have moving along, we have the drive transistor for the sounder alarm, which is at that device there, that transistor there. Next along are the 2 LM35 TO92 thermal sensors. The one on the far left, with again a blob of blue tack on, is the hot one. That would be placed over the black dot on my microwave oven. And on the right hand side, which is under the green wires, slightly obscured, is the cold one, and that will probably sit in one of the corners of the microwave again. Other than that, the reason why there is a blue tack blob on the top of the hot LM35 is that attached to it I've got, I don't know whether you can see it, but there is a resistor attached. Well, that is a heating element which is a 330 ohm resistor, and that is connected over here to a 13.5 volt lead acid battery. And now I will pan out to the overall layout of my demonstration here. I'll zoom back out. You can see the setup here. One is you've got a right hand digital voltmeter here. Well, that's the cold temperature digital voltmeter, and it's reading 0.21. Well, that represents 210 millivolts, which represents 21 degrees C. On the left hand side, the left hand digital voltmeter, you have 0.209. Well, that's very near 21 degrees C, and that represents 209 millivolts. You have the circuit as I've just previously described, exactly the same there. I've made 1 or 2 minor alterations to the circuit as compared with the Falstead simulation. Real life is always slightly different, isn't it, than a simulated one. And on the far left that you can't see, that's not in view, is a 14 amp hour, quite large, lead acid battery. If you use a lead acid battery like this, please ensure that there is a fuse. I've got a 1 amp fuse on the output of this, and the terminals are fully insulated so that if you get a short circuit on here, you can actually extract in excess of 100 amps out of one of these cells for a short while, and that could cause serious damage and possible fire. So it's very good to have this correctly, nicely fused for your own safety and the safety of your home. Okay, so the first thing for me to do is probably check the reference voltage to ensure, as I said earlier, that it's set to 0.5 of a volt, which represents a difference of 5 degrees C. So I'll just unhook that from the that one there, which is the right hand digital voltmeter, and move it across to the reference output, which is there. And there you've got it, 499. Well, that's very close to 500 millivolts, representing 5 degrees C. So I put this back to, this is the cold digital voltmeter. So I put this back to the output of the LM35 cold sensor, and we're now shifted up slightly because the ambient temperature in here, and I have windows with sunshine on it occasionally, that the room does warm up fractionally, so you will see some variation in ambient temperature. Now I'll connect the battery to the heater element, which is that 330 ohm resistor, and we should see, all things being equal, the left hand digital voltmeter, the red digital voltmeter for hot, lift, increase. Now let's just see whether this works. I haven't actually tested this before, so let's see what's going to happen. Oh, there we go. Moving up to 22. Well, it's got to lift up by about to 26, isn't it? 26.3, which is 5%, 5 degrees above the ambient temperature, which should be about now. And there it goes. And as you can see, the little alarm is loud enough, isn't it? If I'd actually not put the little ball of blue tack on there, that would be piercingly loud. So in principle, that's it. Now what I do now is the temperature has gone up to 32 degrees C on that little TO92 package, and I'll disconnect the supply to the heater element. The heater element, of course, will not be included on the little board because it doesn't need to be there. I'm just using it heating up. Now you should start to see this drop down, and of course it's got to drop down to 23.4. This is lifted very slightly, and I've got a feeling it's because of the radiated heat from, I've got these quite close together, it could be radiated heat from the heater element on the hot LM35. So we've got down to, it takes a little while for this to come down. There's thermal mass in here, isn't there? So we just see it drop down. It's going to take a little while. There you are, it's dropped below the 26 degrees C limit. So as far as this demonstration is concerned, I think that's it. The next thing for me to do is to put it actually onto the microwave oven and see whether it works or not. I haven't tested it. I don't know whether it will or not. I had my one or two concerns, and we'll leave that to the day, but when I set it up we'll find out whether this actually does the job or not. I had just a thought, and that is I would calculate the wattage dissipated in the 330 ohm heater element resistor, and the formula, basic formula, as an awful lot of people will know, is V squared over R. So let's go, I'm nudging the tripod a little bit here, but let's go 13.5. This is my Casio FX201P, early 1970s calculator. Let's go next to Y2, and that will equal, there we go, what is it, 182, and let's divide that by 330 ohms and push the equal button, and there we are, just over half a watt. Before we go to the microwave oven and apply this circuit of mine, I thought I would do a quick look at the final circuit diagram. This will be as brief as possible, and I go from left to right. We've got here the heater element, the 330 ohm heater element, which is not included in the final
circuit. The two LM35s, there is a decoupling capacitor. It's wise to include that as close to the terminals, the plus and minus terminals, as possible. There is a slight modification to the differential times 10 differential amplifier, and that is the 47k and 470k ohm resistors have been replaced here with a 100k and a 1 meg. It's still a time 10 gain, but it increases the input impedance here. And of course, a decoupling capacitor, again across the TLC 272, is always wise to do that. No other alterations to the circuit here through the Schmidt trigger. The output, now the power supply to this, the boost converter, what I did here was I removed the sounder positive supply from the 5 volts of the boost converter. It was dragging the 5 volts down a little bit, and as the sounder can operate to about 3 volts, if not slightly less than that, I connected it to the positive of the battery so that when it draws its 22 milliamps, it doesn't take it from the boost converter, it takes it directly from the battery itself. And in that way, it doesn't introduce interference post boost converter. That's about it. The battery pack, of course, is made up of 3 times AAA. I would have preferred 3 times AA, but that's all I had by way of a holder, is the AAA. And the next thing I'll do now is go to the microwave oven.
As promised, here we are in my kitchen cooking up a circuit. The bit that's familiar to us all is the microwave oven. It's switched on. You've got my circuit, the differential temperature sensing alarm circuit, over the back there. That's operating. You have here on the black spot of the microwave oven a LM35 with hot written on it, and on the corner here of the microwave oven you have a cold LM35 in the corner of the microwave oven. Going back down to the digital voltmeters, on the left hand side you have the cold digital voltmeter, and it's reading at the moment 25 degrees C, which is the ambient temperature inside the kitchen here. Thank you very much, nice and warm. And on the right hand side we have the red for hot digital voltmeter reading 24.8. There's obviously a very slight difference here because the microwave oven is actually on. The electronics inside is producing a small amount of heat, and that's being measured at the top there. So what I'm going to do now is open the door and measure the amount of time, start a timer to measure the time that it takes for the alarm, which is set at 5 degrees C, to operate. I won't expect you to sit there looking at this wonderful picture for what could be 5 or 10 minutes. So I switch off the video while that's going on, and I switch it on again probably at 5 minutes, and we'll wait and see when it actually triggers. Bearing in mind that this is set to 5 degrees C triggering. So that's what I do. So opening the door, there we go, and start the alarm, start the timer I should have said, and we'll be back in 5 minutes. Well, there you are. First of all, I must apologise for the ambient noise. Washing machine running, life goes on. But I've got to 5 minutes 57 and the alarm's just fired up. And you can see the temperature on the cold DVM is 28 degrees C, because obviously the cold warms up as well as the centre, but hopefully not as much. And you can see it's reading 28.5 degrees C, whereas the black spot, the hot LM35, is now reading 33. Well, if you add 5 to 28, That will come to 33.5. There you go. So it is working perfectly. I'm still not happy with the transition between non-alarm and alarm. There seems to be some sort of buzz on it, but certainly as an alarm it would certainly remind you to shut the microwave door, so it would have the desired effect. But nevertheless, I would like to improve upon that aspect. So there we are. What I need to do now is I'll reset everything, cool the microwave oven down, and then cook something. Put some water in a jug in there and see how the system works with these sensors in these two positions. I have a feeling that I will be moving them, but we'll see. So here we are back again, and the microwave oven has cooled down to 25.4, slightly higher than it was before, but the kitchen is actually slightly warmer, and at least they are actually both the same. So what I'm going to do now is put in half a litre of water into the microwave and then leave the microwave on for about, I don't know, 4 minutes, maybe 5 minutes. Let's see what happens. Pop that in there. Pop that in there. Set the timer. Let's say 4 minutes. We don't want it boiling over particularly, but there we are. And let's see what happens. I wonder what the results are going to be. Let's push on. There we are. So we've got lots of noise in the room, haven't we? With the microwave oven running as well as the washing machine. But good Lady Beamer doesn't like to stop the world for my videos. So it's for me to put up with. Are we seeing a temperature increase on the digital voltmeter? There's the cold one and there's the hot one. The hot one has lifted very slightly and is continuing to lift. See, if it lifts to 5 degrees C, which is what the differential temperature sensor is set to, then the alarm will sound. What I'm hoping for is the alarm won't sound because the cold sensor is lifting as well as the hot sensor, but not as much. That's my hope. So what have you got your money on? Hot one's climbing. Is the cold one climbing? Yes, it is. The cold one's climbing. Of course, if the cold one climbs as much as the hot one, the alarm will never sound. We won't be boiling over yet in the microwave oven. I'll switch you off for the moment. There's no point in looking at this scene and getting bored, so let me just turn that off. And I'll come back in about 4 minutes, 3 minutes, something of that order. Here we are coming up to nearly 4 minutes in microwaving this half litre of water, and the 2 meters are keeping quite good track of about 3 degrees, 3.5 degrees C. So for 4 minutes of microwave running, this alarm is not sounding, which is the performance that I'm after. But what I would do is I'll do another 4 minutes with another half litre of cold water and see how that works. And okay, for that I'll switch off and come back on again in a second. Well, I don't know whether you can hear that, but as the microwave was cooling down in between me replacing the cold half litre of cold water, the alarm has now sounded. Well, that's not what I want. The difference in temperature, obviously the hot sensor is staying warmer than the cold temperature sensor. The cold temperature sensor is dropping quicker than the hot sensor, and we're getting what, 5 nearly 6 degrees C. So if I set the sensors up here for a difference of say 7 degrees C as opposed to 5, we should find that the alarm won't sound as the microwave is cooling down from cooking. I'll try that. Well, now I've changed the reference voltage from 0.5 volts DC through to 0.7 volts DC. That translates to a 7 degrees C difference. So it was 5 degrees, I've now adjusted it to 7. And what this setup failed on was when the microwave oven was cooling down, the hot sensor was staying hotter than the cold sensor, therefore there became a difference of 5 degrees C and it triggered. Well, let's hope that 7 degrees C does the trick. So I'm now going to run the microwave oven for 4 minutes, and I'll probably switch the video off again and then come back on again when it's reached, or very nearly reached, the 4-minute period. So I'm switching it on now, and I've got half a litre of cold water in there. But here we are, the 4 minutes is up on the microwave. The hot sensor is 40 degrees C and the cold sensor is 37 degrees C, a difference of 3 degrees C. Now then, the alarm obviously hasn't sounded. What I'll do now is take the hot water out of the microwave oven and see how this operates as the microwave oven is now cooling down. Right, taking the hot water out. There we are. And I leave the door open and see how it works. 42 points, still rising. There's obviously thermal mass in there. The cold sensor, is it starting to drop? No, it's still rising. Still rising. Now, of course, I've got to shut the door because the lamp is on, so let's just shut that. So now the lamp is off, it should cool down properly. Okay, well, I'll let you know if the alarm comes on. Yeah, here we go. The alarm is starting to fire because that's at 38 degrees C, which is the cold one, and the hot one is at 45. So there is a 7 degree difference, and the alarm is firing. So on the face of it, this is a failure. But what I would do next as an experiment is shift the cold sensor nearer to the hot sensor, maybe over there, and see what happens. Is the alarm trying to go off? No. Anyway, so that's my next port of call, is to move the sensor and see if I can get an improved situation there. Oh yeah, look, yeah, it's falling below 7 degrees C difference. So the alarm's gone off. I could kind of tolerate that, but it'd be nice if it actually worked perfectly, and I'll see if I can achieve that.
This is Beamer signing out for now.